Since time immemorial, humankind has looked to the stars. The universe has always been a source of fascination and of mystery. How was the cosmos born? What else might the universe contain? And where do we come from? But we also live in permanent danger. Along with us, millions of objects are hurtling through space. Meteorites, comets, asteroids. Some of them we know, others have yet to be discovered. The biggest of them are true killers. If they hit the Earth, it could mean the end of humankind. Welcome to Spacetime, featuring astronaut and scientist Ulrich Walter and an expert on surprises the universe has in store for us. An asteroid is hurtling towards the Earth, a massive lump of stone and metal. We know that it is coming because our scientists have long since discovered it, but we have no chance of stopping it. It crashes into the Pacific with devastating consequences. This end-of-the-world scenario is Hollywood fiction, but the effects of such an impact are totally realistic. We search for asteroids and observe them, calculate their orbits, and assess how dangerous they are. We can even land on them. But not every object coming from outer space is discovered. And when heavenly bodies come too close to the Earth, they pose a real threat.
There are many millions of asteroids. Today, we know thousands of them that cross the Earth's orbit. There can be absolutely no doubt that someday they will hit us. The only question is, are we prepared for it? Can we do anything about an asteroid impact?
At some point or other, a global killer will cross the Earth's orbit. A giant lump of rock from outer space can strike our planet and extinguish all forms of life. And it would not be for the first time. Chelyabinsk in Siberia. On the morning of February the 15th, 2013, a fireball hurtled across the sky. It was a meteor. The meteor broke up over Chelyabinsk, a Russian city with over 1 million inhabitants. It exploded in mid-air.
People first saw something flying across the sky. It was an asteroid, or to be more accurate, a meteoroid that had already slowed down. This rocky body was, of course, super hot because friction caused it to heat up in the Earth's atmosphere.
The object from outer space raced over the region in only a few seconds. The light from it was brighter than the sun. Coming from the southeast, the meteor entered the Earth's atmosphere over Kazakhstan at an angle of 16 degrees. No early warning system had picked it up.
The object measured about 20 meters across. We reckon that a body of that size goes down somewhere on Earth once every 10 to 100 years.
The pressure wave damaged over 3,000 buildings in Chelyabinsk and the surrounding towns. Nearly 1,500 people were injured. Most of them suffered cuts from shattered windows.
How could the Chelyabinsk meteorite strike without a warning? First of all, let me explain the terminology. Small asteroids are called meteoroids, with a D. When they enter the Earth's atmosphere and emit bright light, as they burn up, they are meteors. And if anything still reaches the ground, the fragments are called meteorites, with a T. So the meteorite struck. It came from what we call the ecliptic plane. In other words, at half height, and also from the east. Unfortunately, it was in the morning at 9 a.m. local time. The meteorite came straight at us out of the sun. We couldn't even see it, not even with telescopes. As a result, it was not predictable. That's why no alarm was sounded. A second problem was that it disintegrated in midair. And when a meteorite shatters, it immediately releases its energy because of the many fragments. These create a massive pressure wave. And this air blast and this pressure wave destroy absolutely everything. That's why this meteorite, in contrast to so many others, did not leave a crater behind.
The Barringer crater in the American state of Arizona. 50,000 years ago, it was created by a meteorite roughly twice the size of that hit Chelyabinsk. The crater is over a kilometer wide. The impact destroyed all life within a radius of 4 kilometers. Impact craters on the Moon can be observed particularly well. Unlike on Earth, here they are not eroded by wind and water. The Moon's surface is dotted with craters of all sizes, which bear silent testimony to countless impacts. The Moon lacks a protective atmosphere. As a result, the sustained bombardment from outer space has left clear traces. But on Earth too, many craters are still visible, even though they have been abraded by the weather over millions of years. Up to 250 kilometers wide, the biggest can only be seen from the air. The impact of one of them changed the Earth's climate so much, scientists believe that the dinosaurs died out.
Mankind would survive, but the consequences of a meteorite impact would be catastrophic, with possibly billions of lives lost. But humans can react logically to such an event. We would know what to do. The dinosaurs couldn't.
The final size of a crater depends on the weight of the object and its velocity. On impact, asteroids several kilometers in diameter release vast quantities of energy. An object of that size could penetrate the Earth's crust to a depth of up to 20 kilometers. All life within a radius of several kilometers would be immediately extinguished, but even asteroids measuring less than 1 kilometer across would hit with fatal consequences.
An 800-meter large object would cause what we term regional damage. In other words, an entire region would suffer widespread destruction. On hitting the Earth, just like when it flies through the atmosphere, a meteorite causes shock waves. On impact, the material melts and, above all, is extremely hot. So there is not only a shock wave, but also a heat wave, which simply combusts material at a temperature of several thousand degrees. So that would be fairly unpleasant.
Asteroids have also impacted on the area of modern-day Germany. One that created the Nördlinger Ries in western Bavaria had a diameter of around 1.5 kilometers. It hit the Earth here around 15 million years ago.
The Nördlinger Ries meteorite was of a size that would have had global consequences. We don't know whether it would have resulted in mass deaths, but it would have created vast clouds of dust. We can be grateful that the impact occurred millions of years ago. Today it would be a major disaster that probably couldn't be confined locally.
The impact immediately extinguished all life within a radius of 100 kilometers. At that time, however, human life had not yet appeared on Earth.
Asteroids of that size would, of course, be capable of stirring up so much dust that the amount of sunlight would be diminished for many years. Since farming would be ruled out for many years, it would be impossible to grow food. So naturally, at some point, supplies would be exhausted and man would cease to exist.
Today, there is hardly any trace of the impact in the Nördlinger Ries. The crater has a diameter of some 25 kilometers, only a circular range of granite hills still indicates that enormous forces once had an impact here. It was not until 1960 that American scientists discovered, on the basis of rock samples, that the basin was created by a visitor from outer space.
Depending on its size and how it exploded, the damage caused by an asteroid impact can vary considerably. Let's start with really small objects, with a diameter of 10 meters. It's the kind of impact that happens every 10 years or so. Nevertheless, the impact is equal to that of 10 Hiroshima atom bombs. But why don't we see any evidence of this? As a rule, meteorites come down somewhere in an ocean or where there's no human habitation. That's why we don't notice very much. But if a meteorite is 100 meters in size, a lot more happens. That was the case over a century ago in 1908. An asteroid exploded over the surface of Siberia and flattened 2,000 square kilometers. If that were to occur near Berlin, everyone would be dead. That happens roughly once in 1,000 years. The impact is then equal to 10,000 Hiroshima bombs. The biggest of all is an asteroid around 10 kilometers in diameter. Such an impact occurs roughly every 10 to 100 million years. It happened when the dinosaurs were wiped out. The gigantic force was equal to 10,000 billion Hiroshima bombs. Unbelievable. Mass extinction. Every higher creature on Earth gone. Fortunately, we emerged from that. And there's another small difference. When a solid asteroid impacts, it leaves behind a crater like the one you see here. It measures only a few kilometers across. That's ideal for us because all the energy dissipates locally. If something like that disintegrates in the air, what we call an airburst, the entire detonation force hits the Earth, destroying thousands of square kilometers. And that's the worst thing imaginable.
Humankind is trying to protect itself from such catastrophes. The first step is to localize dangerous objects. Scientists systematically observe everything that is happening in our solar system, like the meteor rain, which our planet regularly flies through. Large objects are observed in particular detail. When they are discovered, their orbit can also be calculated. Danger only threatens if an asteroid's orbit coincides with that of the Earth. Ceres, for instance, is under constant observation. Almost 1,000 kilometers in diameter, it is the largest body in what is known as the asteroid belt. In 2015, NASA sent Dawn to Ceres. The probe mapped the dwarf planet roaming through our solar system and analyzed its chemical composition. Ceres consists of a rock core surrounded by a mantle of ice and a crust of light minerals and ice. Ceres was discovered as long ago as 1801, a giant rocky object, but only one of many.
Ceres was discovered roughly 200 years ago and was originally classified as a planet. That's because it was in a position within our solar system where astronomers actually expected a planet. But after around 20 other bodies were found in the same area, science moved away from the planet classification and said, okay, it's a new object, a new type of object.
But where do asteroids come from? For a long time, astronomers thought they were the result of a cosmic catastrophe when a planet disintegrated. But that theory was refuted a long time ago because the mass of all known asteroids together amounts to a mere 0.1% of the Earth's mass, and that is too little for a disintegrated planet.
Asteroids are remnants from the time when our solar system was formed. Imagine it originally as just a cloud of gas or dust in space, which compressed. This created great heat and pressure at the center. The sun formed. Circling this proto-sun was a vast number of dust particles. When they collided with one another, they became bigger and bigger. This gave rise to the planets, but many other objects were left over.
These objects are now flying through space on their own orbits, and more of them are being located. The number of known asteroids in our solar system rose from 300 in 1890 to the present figure of 700,000. The actual number is probably several million. It is important for scientists to detect as many of these bodies as possible. Asteroids are being studied with telescopes and probes. The efforts and the cost are enormous, but only in this way can any possibly dangerous visitor to our planet be recognized in good time.
Als erstes muss man das Objekt entdecken.
First, an object has to be discovered. A light signal from it is measured and then tracked for several days or even years to determine its exact orbit. As soon as that has been done, the object is given a specific number and entered in a catalog. It can then be predicted when the object will return.
Once an asteroid has been classified, astronomers can compare its orbit with that of our planet and determine whether and when it could pose a threat to us.
Most asteroid orbits remain extremely stable for thousands or even millions of years. But with smaller objects, this can change. Minor forces have a constant effect on them and can easily push them off their orbit. Reactions with larger bodies, the planets, can also occur, resulting sometimes in dramatic changes in the shortest of timescales.
Astronomers worldwide keep these objects under constant observation. ESA, the European Space Agency, also operates an early warning system. Its purpose is to discover and track asteroids and warn of any possible collision. Even a system like that cannot provide absolute safety. Nevertheless, these huge rocky objects are carefully monitored.
The really big objects are already well known. A model calculation of every asteroid up to a diameter of 20 kilometers tells us precisely where it is. And not one of them is on a collision course, so nothing can happen. We're missing a few 10 or 20 down to a diameter of 1 kilometer. We don't know yet where they are, but we will discover them soon, and then they will no longer be a problem. So I believe that in the short term, the threat posed by the large bodies is relatively small. But where do these highly dangerous asteroids come from? In all, there are 3 totally different sources in our solar system. Let's start with the furthest away. If this is the Sun, located a vast distance from it is a huge spherical cloud known as the Oort cloud. When other suns pass it, comets can be set free. But this rarely happens. What we call long-term non-periodic comets are created. They're not so dangerous. Comets and asteroids are far more important. The difference between them is that asteroids contain less water than comets. Because of their water, comets have a large tail, which can be clearly seen. They're formed beyond the last planet, Neptune, where there's a belt of countless fragments known as the Kuiper Belt. Sometimes Neptune shoots or takes a comet out of this belt and brings it back again. If this here is the Earth's orbit, it's obvious that such a comet could hit our planet. There are vast numbers of comets. Halley's Comet, for instance, arrives every 75 years. But they too are not so dangerous. The really important and above all harmful comets come more from the inner orbits. Here, between Mars and Jupiter, there's an entire belt of asteroids. It's actually known as the asteroid belt. It contains millions of asteroids. Sometimes Jupiter, the giant planet out here, can hurl a few asteroids from this belt into the inner area. These near-Earth asteroids, which can cross the Earth's orbit, are of course dangerous. So far we have identified over 1,000 of them. If they cross the Earth's orbit, this could of course result in a collision, especially where the large asteroids are concerned. The asteroids have a characteristic diameter of between 10 meters and 10 kilometers. All those that are fired into this range and cross the Earth's orbit here or here are the really important ones.
If such an asteroid struck the Earth, the impact would be catastrophic. And not only would the point of impact be directly affected, depending on the size of the asteroid, governments and civil defense authorities would have to prepare for worldwide consequences.
I can remember that the disaster control authorities will be informed of an impact likelihood of more than 1% over the next 50 years. Until then, you could say that the authorities are at least in the picture. So nothing else needs to be done. But the level at which measures really need to be taken always depends on each specific case.
The Hollywood movie Deep Impact presented a realistic picture of what such a specific case would mean for humankind.
An explosion of that magnitude would create a gigantic pressure wave which would flatten everything.
In all likelihood, the asteroid would go down in one of the world's oceans, causing a tsunami of previously unknown dimensions. Cities near the coast and their inhabitants would be obliterated. The waters would surge far inland. An impact on land would also have undreamt-of consequences. The asteroid would have an explosive force equal to thousands of atom bombs.
Actually, we're incredibly lucky with our solar system because we have two natural protective screens against asteroid impact. The first consists of Jupiter and Saturn. With their vast gravitational force, they suck in asteroids arriving from far out, from the Kuiper Belt and the Oort cloud, and thus prevent 90% of them from hitting the Earth. Then there's our atmosphere. However, it has not only positive but also negative features. The big advantage is that when asteroids enter it, around 90% of them burn up. So they don't even hit the Earth and cause destruction. On the other hand, when they burn up on entry, they usually cause a huge pressure wave which destroys a great deal locally.
The Earth's atmosphere makes life possible in the first place. At the same time, it ensures that smaller lumps of rock from outer space cannot cause too much damage.
They arrive at great speed and are then heated up through friction in the atmosphere. Some don't even reach the ground but explode at a certain height because of the heat.
At night, these celestial bodies that burn up are seen on Earth as shooting stars. These rocky objects are comets or small meteors.
Basically, shooting stars are the remnants of comets, which lose a lot of dust, a lot of material on their trajectory. The Earth crosses this orbit, and we can calculate with great accuracy when our planet will meet the center of this dust structure. The number of shooting stars is increasing dramatically.
That is also observed here at ALMA, the Atacama Large Millimeter Array in the desert of northern Chile. The biggest assembly of radio telescopes in the world, it entered operation in 2013. Construction of the complex cost more than $1 billion. A total of 66 antennae, up to 12 meters in diameter, were erected in the desert. Interlinked, they can observe the universe more precisely than all the world's observatories before them. ALMA is an international joint venture involving Europeans, Canadians, Americans, Japanese, and the Republic of Chile. The telescopes actually observe the genesis of planets and stars, but they also provide accurate information on asteroids. They function not within visible light, but in the millimeter and sub-millimeter range. They are thus able to discover and track asteroids on the basis of their inherent radiation. The data collected here are used worldwide.
Data on every asteroid observation is gathered at the Minor Planet Center in America. Scientists there then calculate roughly whether the object could be close to the Earth.
When such an object appears, speed is of the essence. Only when its trajectory can be determined exactly do we know whether the Earth is in danger and are in a position to take appropriate countermeasures.
Je früher man einen solchen Asteroiden oder auch Meteoriten entdeckt,
the earlier such an asteroid or meteoroid is discovered, the better.
je früher man das tut, desto
Because then its path can be calculated.
Bahn berechnen. Und wenn der
And when the asteroid gets closer, the forecast can be made more precise. Once a certain probability is reached, then steps have to be taken.
The most important thing is to recognize a dangerous object as early as possible. The next stage is to determine its path. This is then compared with the Earth's orbit.
Further observations are then made by amateur astronomers, for example. These are incredibly important. They see where an object will be the following day or after a week. At some point, I can then predict its orbit so accurately that I can calculate 100 years into the future.
Large objects are usually identified very early on, and a possible collision with the Earth calculated years in advance. But with smaller objects, this is far more difficult. Indeed, almost impossible. And this makes them so dangerous. Scientists try to classify objects according to the threat they represent. One method is to apply the Turin scale.
It's important to know that the Turin scale evaluates the risk of an impact. In other words, the product of the size of the impact damage times its probability. Why probability? Because astronomers do not know the path of an asteroid exactly. It can lie a bit to the right or to the left. To the right, and it would pass by the Earth. That's why there's a scale of 1 to 10. 0 means that in all probability an asteroid would not impact. In other words, 0 damage would result. 4 to 5 indicates local damage with an average likelihood. But 10 means a 100% probability of humankind being wiped out. The worst thing that could happen. Take the Chelyabinsk meteorite. Had it been identified, local damage with a probability of 90 to 100% would have been indicated. 0.3 on the scale.
With more than 500,000 objects in the asteroid belt alone, a killer could appear at any time. Consequently, scientists want to know as much as possible about asteroids. The best place to obtain information is on the spot. In the mid-90s, NASA launched the Near-Shoemaker probe to orbit an asteroid for the first time. In February 2000, the probe went into orbit around asteroid Eros.
Near-Shoemaker was an American mission to the asteroid Eros, the biggest known near-Earth asteroid. So the probe was directly in orbit. This wasn't just a flyby. They were in orbit and observed the asteroid for several months.
The Scout began to explore the asteroid with X-ray and gamma-ray spectrometers. First of all, the probe orbited Eros at a distance of 350 kilometers. Later, NASA reduced the orbit to just 50 kilometers from the surface of the asteroid. The NEAR probe then made a detailed study of Eros.
Just by orbiting an asteroid, I can register quite a lot. I see the exact shape and the number of craters. And from the number of craters, I can calculate the age of the surface and determine whether it's a young asteroid or one that was also formed together with the solar system.
The Japanese Hayabusa mission even went a step further. Launched in 2003, its probe was designed to remove rock samples from an asteroid for the first time and bring them back to Earth.
The Japanese mission Hayabusa was named after a falcon, which seizes its prey in midair. In similar fashion, the probe removed samples and brought them back to Earth. The samples, which weigh only a few micrograms, have now been examined. Eros is one of very few asteroids to be accurately mapped and to have provided our laboratories with surface material.
The Japanese probe's goal was the asteroid Itokawa, which had only been discovered a few years earlier. Surprisingly, pictures from the probe showed that there are hardly any craters on Itokawa. In September 2005, the probe then landed on the asteroid and took samples.
Having a sample brought back from an asteroid is the absolute ultimate goal for a scientist, because it can be examined in the laboratory with machines. If I fly to an asteroid and carry out measurements there, the equipment has to be as light and small as possible.
Having taken samples, Hayabusa set off on the return journey. Despite problems with its ion engines, in June 2010, the probe reached the Earth again. The capsule with these samples was released and drifted down safely, whilst the probe itself burnt up over South Australia.
The Japanese probe described the object superbly in every detail. The asteroid is relatively small, about half a kilometer across. We knew all about its size and the nature of its surface beforehand, but the big surprise was to learn that it is not a solid body. Now, of course, as it has emerged from a 3D printer, it is a solid body, but in reality, it has the density of sand.
That is also the reason for the absence of craters. Hayabusa simply sucked up all the lumps in outer space. ESA also participates in the study of asteroids with its own probes. In March 2004, an Ariane rocket took off from the Kourou World Space Station. On board was the Rosetta probe, bound for the comet Chury. The flight from the Earth to Chury took 10 years. The probe reached the comet's orbit in 2014 and released Philae, the landing module on board. Philae landed on the surface of Chury in November 2014. 17 nations are participating in the mission, which will cost €1 billion. The scientific program is ambitious. The focus is on the Earth's genesis.
When scientists asked themselves where the water on Earth could have come from, they suspected it was brought by comets. The Earth was once so hot that it had no water at all. Consequently, there was a particular appeal in studying comets. And that's why a flight was undertaken to a comet with Rosetta, the European space probe, and with Philae, the landing module provided by several countries.
Since then, Rosetta has orbited the asteroid just a few kilometers above its surface. Comprised of two lobes connected by a narrow neck, the asteroid weighs about 10 billion tons. It rotates once about its own axis every 12 hours. The Rosetta mission is one of the greatest successes of European space research and a milestone in the study of asteroids. And the hunt for rocky objects in outer space continues. In September 2016, the American probe OSIRIS-REx set off for Bennu, a near-Earth asteroid. Bennu is a dark rock with a diameter of roughly half a kilometer, a killer that could come dangerously close to our planet. It is estimated that in the year 2135 it will fly past in close proximity, and on its next visit it could even collide with the Earth. NASA plans to land on the asteroid in order to obtain more accurate data and calculate its future orbit more precisely. Scientists want to find out as much as possible about the asteroids and the dangers they pose. But what will happen if they really do discover a global killer? In Hollywood movies, countermeasures are planned. There, the world's population panics. But what would reality look like?
What would happen if an asteroid impact were imminent? Many people believe that secret emergency plans exist, which we never hear anything about. But there aren't any. There is merely a group at the United Nations calling itself the International Asteroid Warning Network, a worldwide network of space institutes which collects information and then calculates when and where such impacts could occur. So if, for example, an impact were to occur in a month's time, they would calculate the trajectory precisely, work out the point of impact, and inform the general public. There's a slight difference in an asteroid striking Berlin or someplace 1,000 kilometers away, and it's easy to miscalculate, so it's necessary to show a little restraint in making predictions. The group's task is to disperse the information openly. And if you ask me whether we have any form of defense, I must say no, we have absolutely nothing.
Where identifying a dangerous object is concerned, humankind faces a problem. The disaster can be calculated in advance, but a defense plan does not exist.
The biggest challenges facing such a mission would include the time pressure. Every day that is lost makes it harder to fly there with truly great precision and land exactly at the right location.
But what can be done when the probe approaches? Should the asteroid be blown up with a nuclear bomb?
That would be extremely dangerous. Happily, science has moved away from the idea because it's far from simple. It would be hard to predict the actual consequences of fragmenting an asteroid with an explosion.
The worst-case scenario would see the asteroid break up into fragments, each big enough to survive a flight through our atmosphere.
If an explosion really were triggered, it would have to be at precisely the right place and at exactly the right distance from any satellite that was flown there. The result cannot be totally planned, and the effect would not be truly visible for weeks or months afterwards.
But blowing up the asteroid is not the only option. If a dangerous body is discovered in good time, it can also be deflected from its orbit without an explosion.
Basically, you take a really heavy spaceship and fly close to it. Because of gravitational attraction, you would expect the spacecraft to drop onto the asteroid or vice versa. Approach could be avoided by igniting the spaceship's engines in the direction of the asteroid. However, the asteroid would continue to be pulled towards the spacecraft, and you would slowly divert the asteroid from its orbit.
This procedure would take several months or even years.
The asteroid or meteoroid would only be slightly diverted from its previous orbit. In that respect, the mission would be extremely difficult. But in my opinion, the potential success would justify all the effort and financial cost.
A global killer in the form of an asteroid over 0.5 kilometer wide would wipe out the human race. Humankind would not even survive the climatic changes resulting from the impact.
So what's the best way of warding off an asteroid? Well, it depends. Some asteroids are huge, 10 kilometers across. We see them very early, about a year beforehand, perhaps even 2 years. With that kind of size, they cannot simply be destroyed. It's better to divert them because the distance there from the Earth is still huge. So if I divert an asteroid just a little, it will pass the Earth some considerable distance away. We would have to direct a laser beam at its surface. The ablated material would then push the whole asteroid to one side, like a rocket with the thrust principle, and cause it to fly past the Earth. The situation would be totally different, though, with a smaller asteroid, one just 100 meters or 1 kilometer in diameter, which we had seen only a few months or days before. It really would have to be blown up and destroyed, so we would need a rocket with a bomb to fly to it quickly and destroy it. But a lot of people are afraid that the fragments would fall to Earth and kill lots of people. That risk is not too great. Why not? Well, an asteroid is nothing more than a slag heap, a loose pile of rubble. If I blow it up, I will only create millions and millions of bits of gravel. Many of them would fly past the Earth. And because they would be so thin, they would vaporize in the atmosphere. Hardly anything would come down. So that would be the ideal method.
NASA and ESA want to carry out a defense test together on Didymos, a binary asteroid. The aim is to divert Didymoon, the smaller of the two objects, in order to force its larger twin out of its orbit too.
It's about trying on a small scale to see what we could do if such a body were approaching the Earth.
Didymoon is to be the target.
At some point, the DART, an American impactor, will be brought up to fire at the smaller asteroid. This will make it a little bit faster or slower, and as a result, change its orbit.
The decisive question, however, is just how great will this orbital change be? The mission is only at the beginning stage, but NASA carried out a similar expedition back in summer 2005. The target was Tempel 1, a comet with a diameter of 6 kilometers. A NASA probe bombarded Tempel 1 with a fridge-sized projectile. It struck at a speed of 37,000 kilometers and left behind a crater 150 meters wide and 30 meters deep.
The impactor would weigh a few hundred kilograms. With this comet mission, we'd be talking about 370 kilograms of copper. Why copper? So that we know exactly what is being fired into the asteroids. The orbital period of the two asteroids is several hours, 12 hours or so. Through the impact, this will change by a few minutes. Just how much will then show us how our model calculation can be compared with reality.
But research into asteroids doesn't serve just to protect us from catastrophes. As so often in space research, it produces surprising discoveries.
NASA and ESA both have major programs for basic research in space, but also for developing new technologies. We want to know, for example, how our solar system originated. How were the smaller planets like Earth, Mars, and Venus formed? Why are we here? Other stellar systems do not contain any planets similar to Earth. To accomplish this, we need to study the beginnings of our solar system. Rosetta is a fine example. In Rosetta, we have studied a comet which could have brought life, but above all, water to Earth. We flew there. We saw water. Yes, this comet had water, the very water we have on Earth. Not precisely that water. In other words, lots of comets must have brought water to Earth, and that's how our oceans were formed.
Aber nein, so entstand unser Ozean hier auf der Erde.
How expensive was the mission? Well, it wasn't cheap. The whole Rosetta mission cost around 1 billion euros, with a preparation period of 10 years and a 10-year mission. That worked out to be around 50 million euros a year. But let's look at other projects. Take the huge CERN particle accelerator in Switzerland. It costs 1 billion euros a year to operate. And what do we get out of it? Well, a Higgs particle, for example. What I want to say is that you can't insist on something being obtained directly for every euro invested. And indeed, the fact is that we generate knowledge. We're understanding our world better. We're understanding why we are here. We're understanding where our oceans come from. Because without oceans or water, we cannot survive. This knowledge is extremely valuable to us, not only in space, but everywhere on Earth, even Higgs particles. But space research isn't only basic research. It's also technological development, and we need that on Earth. Otherwise, we wouldn't have all our television satellites and navigation satellites. In particular, though, we will need these technologies to ward off asteroids streaking towards the Earth, which could destroy humankind. That's a wonderful application that doesn't exist anywhere else.
And something else makes asteroids interesting for humans. It concerns the mining of raw materials. The aim is for astronauts to travel to distant celestial bodies as miners, so to speak, and obtain mineral resources. In other words, mine rare metals in outer space. The material would have to be transported back to Earth, an extremely expensive route. So far, there is absolutely no technology for this. It's science fiction, but entrepreneurs are thinking seriously about it.
You can't simply fly to an asteroid and start digging. That's not the way to go about it. What we need are intelligent, eco-friendly mining methods we could confidently take to an asteroid or planet without leaving a desert behind us. Let's call it a desert, even knowing, in fact, it already is basically a desert.
Mining on an asteroid is stirring the imagination of investors and soldiers of fortune. An asteroid only 30 meters wide could contain platinum worth billions of euros. And so developments are being driven not only by humans' curiosity, but also by the desire for profit. As soon as it is profitable and the appropriate technical prerequisites have been created, gold diggers will set off into space and prospect for precious metals. They plan to take possession of comets and exploit them, just like the oceans on Earth are exploited for oil. The plan is to build entire factories in space. There are no limits to the imagination. The Europeans once sailed the 7 seas for spices, settlers conquered the US West for gold and oil. Yesterday it was ships, the railways or pipelines that made profit possible. Tomorrow it will be the spacecraft.
We can forget about that for the next 10 years, I'd say. In 50 years, maybe. But it will be worth the effort.
But science is still mainly concerned with the development of protective mechanisms against dangerous objects from space.
If something comes flying towards us, then it will be here in a few years' time, perhaps 10 years, depending on how fast it is. So we're talking about relatively short time periods. I don't think we're at all prepared. If it did happen, that would be the trigger, so to speak, which would see us all working together to manage the situation.
As things stand, we have no means of protecting the Earth from an object from outer space.
In 10 years, I reckon we will. I'm confident that we could deflect an asteroid. I'll be able to give a definite answer in 10 years' time.
But by then, it could be too late. The question is simply, when and where will a killer come from?
A forecast is practically impossible. There could be surprises, of course, but I reckon that we have relatively large areas well covered already. However, the danger can't be ruled out entirely, of course.
But there is no question that at some time or other, the Earth will be hit again.
So what are we left with? Well, we know it will happen, in a few hundred years perhaps. A small town with the loss of a few thousand lives. In a few thousand years, maybe a big city like Berlin or London with a few million deaths. And then humankind will wake up. People will understand that there's a real problem. Can we do something about it? Of course we can. We need to observe these asteroids. Where are they? And how many of them are there? We need to catalog them. Then we will know how dangerous they are and when they might hit. And then we need a rocket. If we know that an asteroid might strike, we could launch the rocket and destroy or deflect the asteroid. Then the danger would be averted. But as always, something will first have to happen before humankind wakes up.
Perhaps the global killer is already on its way to us. A rotating mountain range from outer space which is destined to wipe out humankind.